Welcome back to the deep dive. Today, we are really putting our chemistry knowledge to the test.
We certainly are.
Our mission is a deep dive into the world of organic synthesis, specifically Chapter 29 of your course book. We're talking about how modern drugs are actually made.
Right.
And we're not just listing facts. We want to answer three big questions for you. First, why does the 3D shape of a molecule matter so much in medicine?
A huge question.
Second, what are the main industrial strategies to make sure you only get the right shape? And finally, how do chemists even begin to design these molecules?
It's a fascinating puzzle. And it's where chemistry, it becomes real.
Yeah.
We're talking about designing molecules to fight disease.
So it's not random.
Not at all. Chemists act like molecular architects. They have to predict the exact 3D shape a drug needs to fit into and block the active site of an enzyme that a pathogen needs to survive. It's all about that fit.
That sounds incredibly difficult. How do you even start to predict something so complex? It feels like it would take forever with just trial and error.
And it used to. But that's where molecular modeling, computer-aided design completely changed the game.
Okay, so tell us about that.
Well, historically, you'd synthesize dozens, maybe hundreds of different compounds in the lab and just test them, see what works.
Wow.
Now, a chemist can identify the features a drug needs, the right shape, the right size, the right chemical groups, and then use a computer to see how well it fits into the target site before making anything.
So you're virtually docking the drug.
Exactly. You're checking the fit. The drug has to form strong enough interactions, hydrogen bonds, ionic attractions, all those forces we've talked about.
It has to stick in there and jam the lock, essentially.
That's the perfect way to put it.
Yeah.
And the efficiency gain is just staggering. A great example is HIV protease.
An enzyme the virus needs.
Crucial for its life cycle. Back in 1988, scientists mapped its structure using X-ray crystallography.
So they finally had a picture of the lock.
They had the blueprint. And with that, researchers could start building inhibitor molecules right there on the computer screen, designing them to block that active site perfectly.
And the results.
Game-changing. In less than 8 years, we had multiple antiviral drugs. It led directly to a massive drop in AIDS death rates. Structure prediction was the shortcut.
That's incredible. And that leads us perfectly to the most important structural feature in all of this, chirality. The vast majority of new drugs have at least one chiral center. And just to jog our memory from Chapter 14, a chiral center is a carbon atom bonded to 4 different groups.
Which creates 2 isomers that are mirror images of each other, but you can't superimpose them. We call them enantiomers.
Like your left and right hands.
Precisely. And here's the problem for industry. A standard organic synthesis, if you don't control it, just gives you a 50-50 mix of both.
The racemic mixture.
The racemic mixture. And what's so fascinating is that even though their basic chemistry is identical, their biological activity is usually completely different.
So if the receptor site in the body is shaped for the right hand, the left-handed molecule is.
It's useless. Or worse, it could be actively harmful. This is why something like 80% of all new patented drugs have to be single optical isomers.
It's a huge economic issue too, right? I mean, if half of what you're making is inactive, you've just doubled your cost.
Exactly. For the patient, a pure drug is twice as potent, so you can cut the dose in half. That means fewer side effects.
And for the company.
It cuts production costs, and crucially, it protects them from legal action if that unwanted enantiomer causes damage.
And this isn't just a theoretical danger. We have real examples.
How do you do?
Naproxen, for instance. One enantiomer is a great arthritis pain reliever. The other one can cause liver damage.
Stark difference.
Or a tuberculosis drug where one version is effective and its mirror image can cause blindness. You absolutely have to get this right.
Which brings us to the core of section 29.2. How do chemists actually get that one pure enantiomer? There are really 3 main strategies.
Okay, what's the first one?
The first is method 1, optical resolution. This is kind of the brute force way.
Make the mix first, sort it out later.
That's it. You synthesize the 50-50 racemic mixture, and then you separate the 2 isomers. To do that, you use something called a chiral auxiliary.
Okay, a chiral auxiliary, what's that?
It's a pure enantiomer of a different compound, and its job is to react with only one of the isomers in your mixture.
Ah, so it picks out the one you want.
It does. It forms a new product, and this new product has different physical properties, like its solubility.
And because the properties are different, you can physically separate them.
Right. Often through a process called fractional crystallization. You might have to do it over and over to get it pure. Then you remove the auxiliary, and you're left with your pure drug.
That sounds Really time-consuming and wasteful. You're still making the 50% you don't want and using all these extra chemicals and solvents.
It is. It has major sustainability issues. That's why chemists are looking for better ways. One innovation is using supercritical carbon dioxide as a solvent.
Supercritical CO2.
Yeah, you heat CO2 to just over 31 degrees Celsius and pressurize it to 73 atmospheres. It becomes this amazing, non-toxic, recyclable solvent.
Yet you can fine-tune it.
You can. By changing the pressure, you change the density, which changes the solubility of your compounds. It makes separation much cleaner and greener.
That's a clever solution. I think the book also mentions using HPLC, right? High-performance liquid chromatography.
It does. If the stationary phase inside the column is itself optically active, it can separate the enantiomers as they pass through.
Okay, so that's method one. What's the more elegant approach?
That would be method two, the chiral pool. The logic here is, why bother separating them if you can just start with the right shape in the first place?
So you find a starting material that's already the right shape.
Exactly. You start with naturally occurring compounds that nature already provides as a single enantiomer. Things like carbohydrates or amino acids.
The so-called chiral pool.
Right. And then you design your whole synthetic route to preserve that specific 3D shape all the way to the end product. No separation needed.
Much smarter. And what's the third method? The ultimate goal.
The ultimate goal is method three, using chiral catalysts and enzymes. This is about controlling the reaction from the very beginning.
So you ensure only one enantiomer is ever formed.
Precisely. You use a chiral catalyst. For example, a very expensive ruthenium catalyst is used to make single enantiomer naproxen that guides the reaction to produce only the one desired product.
And you don't need much of it, I imagine.
Very small quantities, and you can often reuse them. Even better are enzymes biological catalysts. Their active sites are naturally chiral, so they are incredibly specific.
And that's a greener approach too, usually.
Often much greener. It might take longer to develop the process, but it usually means fewer steps and less waste in the long run.
All right, this brings us to the final big piece of the puzzle. Section 29.3, actually designing the synthetic route. This is where you, the learner, have to bring it all together.
Yes, and this is where chemists think in a slightly unusual way. They work backwards.
Retrosynthesis.
Retrosynthesis. You look at your final target molecule and you ask, what chemical reaction could have made this? And then you look at that precursor and ask the same question again and again until you get back to a simple, common starting material.
Like something from crude oil.
Or a compound from a plant. And the goal is always to find the path with the fewest possible steps.
Why is that so important?
Because you lose material at every single stage. Yields are never 100%. So if you have a 10-step synthesis, your overall yield can be tiny.
So your knowledge of all the different organic reactions, that's your toolkit for planning the route.
It is. And one of those common problems you have to solve is how to add carbon atoms.
Right. How to make the carbon chain longer.
Yes. If your starting material has, say, a 2-carbon chain, but your target needs 3, you need a reliable way to add that extra carbon.
And the key reaction for this is converting a halogen alkane into a nitrile.
Absolutely essential. The R halogen becomes an RCN. That nitrile group, that C triple bond N, adds 1 extra carbon atom, just like that.
And once you have the nitrile, you've opened up 2 really important pathways.
2 very different, very useful pathways. If you want to turn it into a carboxylic acid, you hydrolyze it.
Which means refluxing it with dilute hydrochloric acid.
Exactly. But if you want to make an amine, you have to reduce it. And that requires a really powerful reducing agent.
Like Lyl H4 in dry ether.
That's the one. So you have this fork in the road, all starting from the nitrile.
We should also quickly mention the Friedel-Crafts reaction for adding carbons to a benzene ring.
A key reaction for aromatic synthesis, yes.
And finally, a note on analysis. When you look at complex molecules like aspirin, they often have groups that will break down if you reflux them with acid. That reaction is, again, hydrolysis.
It is. Understanding how molecules can be both built up and broken down is key.
Okay. So, to wrap this all up, what are the key takeaways for the learner?
I think there are 2 big ones. First, chirality is absolutely fundamental to modern medicine. The need for a pure, single enantiomer drives a huge amount of industrial chemistry.
For safety and for potency.
For both. And second, organic synthesis isn't just memorizing reactions, it's a strategic puzzle. It's about working backwards retrosynthesis and using key steps like adding a nitrile group to build complex molecules efficiently.
So, for you, the learner, mastering these reactions isn't just an academic exercise, it's literally the toolkit you would use to design life-saving compounds.
That's exactly.
And as a final thought for you to take away, we talked about the dangers of unwanted enantiomers. The importance of stereochemistry really cannot be overstated. I want you to go and reflect on why the drug thalidomide resulted in such massive legal action against its manufacturer. That tragedy is a direct consequence of the very same principles we've explored today.
A powerful reminder.
Until next time, keep digging deeper into the chemistry that shapes our world.